Welcome back. We're going to explore in the last part of this course some properties of this moment map that I introduced a couple of lectures ago. So if you recall, the moment map is a generalization of the way Hamiltonians act or generate vector fields in symplectic manifolds to the case where the group acting on the manifold is no longer the abelian group R or the circle S1, but the group acting on the manifold is instead some compact Lie group. So that's the purpose of the moment map. It captures the idea that the vector field generated on a symplectic manifold comes somehow from a Hamiltonian. But this Hamiltonian obviously has to be augmented to capture all the possible different directions that the Lie group can act on a symplectic manifold. So just to recall the setting, so we call this tuple of a symplectic manifold, a symplectic two-form omega, a function mu and a map psi. We're going to call this a thing called a Hamiltonian G-space. We introduced this notion several lectures ago. And we call it such a thing if there exists this map mu going from the manifold M to the dual of the Lie algebra of the group G, and this map here has to satisfy some properties in order that we can say it's like a Hamiltonian for a non-abelian compact Lie group, for example. So it has to satisfy two properties. The first one is that d mu of x indeed generates a symplectic vector field. And this mu of x at some point p is what you get when you put in an element of the Lie algebra of the group big G. So this is just some function on the manifold M, and it behaves like the Hamiltonian for the one parameter group generated by this element of the Lie group here. And this x hash is the vector field it's the one you get when you take the action of the one parameter subgroup of the big group G acting on M. So there's this psi here. Psi is this map from G cross M to M. And I should put that up a bit. Psi maps from the Lie group to some symplectomorphism of this symplectic manifold. So this is the first condition that this moment map mu has to obey in order to be called a moment map. There's another condition. Second condition that we need is that if you compose it with the symplectomorphism generated by some element G of the group big G, then that's the same as the coadjoint action of G. And remember, under certain conditions, this is actually equivalent to saying that mu is like a homomorphism between two Lie algebras, namely the Lie algebra of the group G and the Poisson algebra of the constants generated on the manifold M. So this is just a reminder of what is this thing called a moment map. Now, because a moment map is very much like the Hamiltonian, it's like an all-purpose Hamiltonian. You give it the direction you want to flow in, and the moment map will give you the effective Hamiltonian that generates that vector field. You'd expect some properties that are familiar from Hamiltonian dynamics to hold also for this more general map mu. And indeed they do in various ways. So today we're going to look at symmetries. And in particular, we're going to explore what happens when a system, a moment map, when the action is symmetric in a certain way to be specified, how we can reduce the effective phase space of the system. So it's a common theme in maths and physics that if you have a symmetry, you have two options. You either can spend the symmetry to reduce the number of parameters you need to explain the system or the equations that you have, spend the symmetry, but that often leaves you with a kind of nonlinear dependence on the remaining variables. That's a typical outcome of spending a symmetry. Or you can retain the symmetry and then you have to express everything up to gauge or using invariant quantities that can't tell if the symmetry is there or not. So today we're going to look at the consequences of spending symmetries when you have a moment map mu. Can you even spend the symmetry to reduce the number of dimensions or variables that you need to specify a point in your system? And the answer, of course, is yes. And this is captured by a very important theorem due to Marsden, Weinstein, and Meyer. I have no hope of proving this theorem. The proof is actually rather, extremely involved. There's a lot of steps. I'll give you an example of its application as a kind of quasi-argument for why it should be true. But the proof of this theorem is definitely beyond the scope of this course. So we've got a Hamiltonian G space. Now it's not just for any group G, it's for compact Lie groups. Now it's quite a lot of the results that we'll discuss towards the end of this course will have the flavor that they're in their nicest form when they're applied to a compact Lie group, but all the examples that we know will come from when the Lie group's actually non-compact. So we'll see this happen a lot. Although I will always write compact, often these results hold in the non-compact case with a couple of sort of extra additional conditions, and furthermore, although it's not, you've got these conditions in, and the theorem finds its expression in its nicest form for the compact case, actually the examples we care about will always be for the non-compact case. Now, we need a candidate for a space that's symmetric enough that we can somehow spend the symmetry. So the theorem here tells us such a space. It gives us a candidate for such a space. And it's this. So take the moment map and find the pre-image of the element 0 inside M. So if we look over here, the moment map mu is a map from M to the dual of the Lie algebra G. So in the dual of the Lie algebra G, it's a vector space, so there's certainly an element 0. So the pre-image of that is some set inside M. Now we know something very nice about the pre-image of 0. Namely, the group G acts quite nicely on it, right? Because if you take, because of the second axiom here, if you take psi G acted on the pre-image of 0 and then apply mu, then using this fact here tells us that that space is invariant, roughly speaking. So that's a pretty symmetric set inside of M. Now, we're going to identify that set in M via this map inc. So inc is just the inclusion map. We're going to make some assumptions. We're going to assume that G acts freely on this funny set mu minus 1. What does free mean? Well, it means that if G fixes some point x, that implies that G is the identity. That's what free means. So suppose all that then, and then we're going to have the statement of this result. then three things happen. So the first thing that happens is already very striking. If you take this pre-image of the element 0, not only is this set have some nice structure, but when you look at the orbits of all the points in this set mu minus 1, 0, and look at how they behave under the action of G, and then identify all points on an orbit down to 1 point, so you quotient out by the action of G, then you get not only a special set, you get a manifold out. So this is, whenever you see a result of the form something quotient something has a nice topological structure, you know something special is going on, because in topology, when you take a topological space and you quotient out by something, often some quite nasty things can happen at exceptional points. So a cone, for example, is a good illustrative case where you have some symmetric action, you take some quotient, you have some topological space, you take some quotient in the topological space, and you end up with something that looks locally nice, but there are some exceptional points, namely the conical singularity that you introduced when you made the identification to build the cone. So quotients usually behave badly in topological spaces, but here we're learning that this particular quotient doesn't behave badly. It's in fact as nice as can be. It's a manifold. The second one, the second condition, well, I'll actually give the definition of this in a second, but I'll put it in brackets because we're not going to pursue this. I will give you the definition of a principal G bundle in a second, but this is not something that I'm going to dwell on in this course. So not only does this mu minus 1 of naught have a nice structure, its quotient has a nice structure, but this also tells us that locally mu minus 1 of naught looks like, locally, a product of some base space, namely this guy, and the group G itself. That's what this sentence there is saying. So we know it's a manifold, but what kind of manifold? Maybe it's just some boring manifold with no structure. Well, no, we get more. There is a symplectic form on this manifold. And the place you would look for the symplectic form, well, M reduced, somehow a subset of M, right? I mean, mu minus 1 of naught is a subset of M, and then you quotient, so somehow this is inheriting something from M. Well, the place you would look for to get a symplectic form then would be to just pull back a symplectic form that you know. And then project out by this quotient operation here. So this is pretty awesome, right? You start with something, a symplectic manifold, you have this nice smooth action on it, but there's no guarantees that if you quotient out by the orbits of this action, that you'll get anything nice coming out. Because it's a quotient. Chaos can break out when you take quotients. But here we learn that none of these things happen. In fact, it's as nice as can be. What you get out is absolute canonical, what your canonical guess would be for this reduced symmetry spent case here. So the way you think about M reduced here, this is what happened when you spend the symmetry, right? You had the symmetry there, this thing was an invariant, it is a space that gets mapped to itself under G, and then you spend that symmetry, and then you have a lower dimensional space with which you can parameterize all the states of the system. So this is your reduced phase space here. We'll take a look at this an application of this to mechanical systems towards the end of the lecture. Before I go on, I'll just give you the definition of a principal G bundle for completeness. The definition can be stated pretty easily, but we're not going to go into connections and that stuff in this course. So another comment is it's sort of hard to find low-dimensional examples because if you have, say, the harmonic oscillator with S1 acting on it, then mu minus 1 of 0 is just the point 0. So everything's obviously true, but in a trivial way. So you've got to look for slightly higher dimensional systems before this becomes non-trivial. And indeed, in our example argument for this theorem, we'll take a look at a 4-dimensional mechanical system. Before I do that, I'll just give the definition of a principal G bundle, because it may, I haven't decided whether or not I'll even sketch the proof of the theorem I'll mention in the next lecture, but if I do, it will definitely mention the words principal G bundle. So let's put it down so that you have it for completeness. So a principal G bundle over B called the base space. What is it? Well, it's a manifold. So whatever a principal G bundle is, it's a manifold. So it inherits all the structure you know from manifolds straight up. But it's a manifold with extra structure. So there's a thing called the projection map, which maps from P down to B. And this map obeys some conditions. Well, quite apart from this map, a principal G bundle is something that admits an action by this group G. Oh, I didn't say that G was a Lie group. I'll do that here. So G is a Lie group in this definition. And I didn't say that B was a manifold, did I? Over B, I haven't said anything about B yet. It's a manifold. So secondly, B is the orbit space for this action. And pi is the orbit to point projection. That's one final condition. Okay, I'm not going to fit it there, so I'll draw a picture in the remaining space. So you think of, here's some manifold B. P is some manifold, and B lives in it, so to speak. So P is like a higher dimensional manifold that contains B, and every point in B has an orbit, right? G can act on any point in B. There's G acting on it, for example. And this manifold B is what you get when you collapse each orbit down to its representative point under the action of G. So that tells you something already, doesn't it, right? It says that you don't have a situation like this with these orbits crossing. So you already get a sense that a principal G bundle is very, very locally, extremely very locally at least, like a product of the base manifold B and the action of the group G. And because the action is free, then you may as well think of this as the group G. And we're going to upgrade this extremely very local observation to a local observation. So yeah, the third condition to be a principal G bundle is condition C. So you can cover B, this base space, with a bunch of open sets such that for every open set U in the cover, there's a map phi depending on U which takes that piece of this principal bundle. So here's what I'm trying to indicate here is an open set in B, and pi minus 1 of U is a chunk of this principal bundle there. You uncollapse the orbits. So there's a map that takes this uncollapsed set of orbits from B into a Cartesian product of the open set and the group G. So it straightens them out, if you like. And this, to express that locally trivialization or straightening out property, we can write it like this. Right, this completes the definition of a principal G bundle. Occasionally touch upon it, I think, in the coming lectures. So condition 1 says that G acts freely on P. That means if a point in P is mapped to itself under the action of G, then that element that did that was the identity. The second one says that B is the orbit space for this action. So at least for a given point in an orbit, you can think of this as being a cross product of the point and the copy of the group G. And then condition C says that that actually holds for a finite region around any point. And furthermore, you can locally trivialize these blocks into a product of the open set and the Lie group G.
Sorry, but what are these maps as U?
These maps are determined by the map phi U in order to get this mapping to work out, and they're a map from from P to G, the Lie group G. So this piece that you focus on here may not be obviously a product of U and G, but when you deform it smoothly, then you can make it locally exactly a product of, or a subset of a local product of U and G. So returning to this Marsden-Weinstein-Meyer theorem, we see that the reduced space has this very particular property that it's the orbit space for the group action, and furthermore, around open sets, it's locally trivial, which is a fairly striking statement here. So the mu minus 1 of naught is a principal G bundle. So it's a manifold itself. M reduced is the base space. And locally, it looks like copies of M reduced times by the compact group G, compact Lie group G. We're going to give this thing a name. What happens when you spend the symmetry in one of these systems? And it's called the reduction. Or the reduced space. It's got multiple names actually. Or symplectic quotient. And there's many more names. So as I said, this theorem is rather involved. The proof technique uses a lot of ideas from bundle theory and also some clever tricks. It's certainly not going to cover it. It's definitely beyond the scope of this course to cover the proof of this theorem. But what I'll do is instead I'll just illustrate it by example, just so you get a sense of what it looks like. So we're going to go for the smallest example that's non-trivial. So if we have a two-dimensional symplectic manifold, then the quotient is trivial always. If it's, either it's trivial in two kinds of ways, but it's trivial. So you've got to go for the next smallest symplectic manifold, which must have dimension 4, because dimension 3 is out, right? We need even dimensions. So let's take it to be a 4-dimensional manifold. And the most trivial compact Lie group that we can get our hands on is S1. So the moment map, whatever it is, you can just think of it really as a map from M to R. The moment map is a map from M to R. And R because that's the Lie algebra of the group S1. So we take the pre-image of the element 0 in M, some one-dimensional space. Sorry, it's some three-dimensional space. And we'll let P be a point inside of mu minus 1 of naught. So we know by the theorem that this is a manifold. Going to try and understand its structure. Do we have these orbit spaces? Do we have that it's a G bundle? Is there a symplectic form? In fact, we're just going to focus on the symplectic form part of the argument. So for a generic function, it must be a three-dimensional manifold, mu minus 1 of naught, right? This is this is one of the level sets of this function, mu. So they cut out one dimension. So we're going to choose coordinates for this argument. And we're going to choose special coordinates in order to observe the structure that this theorem guarantees us. So we choose a coordinate theta along the orbit of P. So P has some orbit under the action of the group S1. So this is some circle inside mu minus 1 of naught. We'll have another coordinate. We'll have the moment map itself. That's a good coordinate. And certainly on mu minus 1 of naught, this manifold, submanifold mu minus 1 of naught, that coordinate's always 0. And we have two remaining coordinates that we would need to fully coordinatize M, namely the remaining two coordinates that you have on the space here, mu minus 1 of naught mod S1. So that drops it down by dimension, drops this dimension by 1, so you know that there's two coordinates on that space. So you pull them back on to M. So now we've got four coordinates. I'm certainly taking it for granted that mu minus 1 of naught is a manifold, that this quotient is a manifold, that it's a principal bundle. I'm just focusing in this argument on the symplectic structure. So it's certainly not any kind of proof, it's more like an illustration. So you can write the symplectic form on M now. We've got coordinates. Just write out the most general symplectic form possible in terms of those four coordinates. So the most general symplectic form on a four-dimensional space in terms of some bunch of coordinates is this: d theta wedge d mu plus bj d theta wedge d eta j's plus cj d mu wedge d eta j's and the remaining two coordinates wedged together, eta 1 and eta 2. So there's a sum over the j here. The most general symplectic 2 form. And then we're going to just note some simple facts and we'll find out that it has the form we want. So if you take the interior product of the vector field dd theta on omega, you should get d mu. So that already tells us quite a lot, right? It tells us that A is equal to 1 and the B's are 0. We know it's a symplectic form, but do we know if it's a pullback of this symplectic form on M red? We don't know yet. But we've got some data now. So it might be that the symplectic form isn't a pullback of the symplectic form on the reduced space. That's how this could go wrong. So we're going to see it's not the case. In this very simple example. So because of this property here, we already know that this term is gone. The only other one we've got to really focus on is the C's. And the D. So again, we use the fact that omega is symplectic, and that just forces D to be non-zero. Now that we've eliminated the B's, we have no choice. D has to be non-zero in order for this to be symplectic 2 form. But that's what we really needed to infer that this is a pullback. We needed that this term was non-zero here. I'll leave that as an exercise to sort out that detail. So this theorem tells us that if you have a symmetry, if you have a manifold that admits some symmetry action G, then you can reduce that symplectic manifold down to a smaller one that's equivalent to spending symmetries in physics. And that smaller space we call the reduction or the reduced space. And it happens to be a symplectic manifold as well, which certainly wasn't a given. So now we know we can reduce, we can spend symmetries. Let's progress on to the more sort of common application of symmetries in mechanics, namely the Noether principle. So this plays an extraordinarily important role in high energy physics because we use the Noether principle to identify symmetries with conserved quantities, and these conserved quantities in turn as the generators of those symmetries. And that's really the connection between the classical world and the quantum world at the high energy physics level. The symmetries, you can find a quantum version of what it means to be a symmetry. It means a unitary representation of a Lie group. And you can find a quantum analog for what it means to be a conserved quantity. That's something that commutes. Or at least the Lie algebra of these objects obeys the Lie algebra of the Lie group. And the Noether principle says that these two things are connected. And that allows us to say when we have some high energy physics system whether or not it really is, say, a relativistic system. It's a relativistic system if it's a unitary representation of the Poincare group and it's conserved. And how do we tell that? Well, the way we typically do that in high energy physics is we go the other way. We find a whole bunch of conserved charges that have the right Lie algebra, and then we say, well, fantastic, we just exponentiate them, and now we have a unitary representation of the Poincare group. And this is a legitimate relativistic quantum theory. But the Noether principle has its basis in classical mechanics. And the most general expression of it would involve these moment maps and G spaces. So as I said, in high energy physics, G is usually the non-compact group, the Lorentz group or the Poincaré group. So we assume we have a symplectic manifold, which is phase space, with a symplectic action of a Lie group G, compact Lie group G, a corresponding moment map mu, and the actual action itself. Suppose we have such a thing, then the Noether's theorem says that a function which you should think of as a conserved charge so if you have some function on phase space, M is phase space, so it's an observable, first of all. If it's a G invariant, so if it's symmetric, then it is so if and only if the moment map is constant So it enjoys a joint role, a joint interpretation here. F is like the conserved charge, or the observable corresponding to the conserved charge. It's G invariant. It's invariant under this Lie group action if and only if the moment map itself is constant on the trajectories of this vector field generated by F. So here we think of F as both being a conserved charge that generates a flow. So what's the typical F to think of? We'll think of like momentum in the case of the group, I don't know, either the Galilean group or the Lorentz group. F is like the momentum. Momentum is conserved, or is the momentum is G invariant if and only if the energy is constant on the trajectories generated by momentum, so it translates. So actually, we already know how to prove this theorem. We've done it for the case where mu is just the energy. We've already actually given this proof. And we're going to extend it now to the case where mu is a moment map for a compact Lie group G. And in fact, there's nothing really to extend. We're going to use exactly the same steps in the proof. Yeah, I quoted a theorem very similar to this when we were talking about integrable systems. So step one is to look at the vector field given by F. How do we get that? Well, recall that you take the symplectic 2 form and define the vector field nu of F by demanding that the interior product of nu of F with omega is exactly dF. Now we're going to let x be an element of the Lie algebra of the group G, and define mu x as before. To be the Hamiltonian function of the G action on the symplectic manifold M. And we're just going to look at how does this function change under that vector field nu of f. So the change of this function here is the same as looking at the Lie derivative of that function with respect to nu of f. It's the directional derivative of this function. And then we use the identity that we already know about. For the Lie derivative of a function. So the Lie derivative of a function is id. The di doesn't happen because the interior product of a function with a vector field is nothing. But then we use this definition, here, to undo d mu of the d of mu x. Now we've got two interior products against the symplectic 2 form. If we did it in the opposite order, we get a minus sign. And now we can use this fact up here. So interior product of mu f with omega, we have a name for that. It's df. And then we undo the definition of the Lie derivative here. And then we do that for all x. So this is 0 because f is G invariant. So f doesn't change if we do a flow on the manifold under some element of G. So it's got to be 0. And now that since that's true for all x, and this is a linear function of x, then we know that mu must be 0. Constant, sorry. So this gives us a generalization of the notion of the integral constant of the motion. If you have a G invariant function, Well, just by analogy to the Hamiltonian case, if you have a function that doesn't change under the Hamiltonian dynamics, then it's called an integral of the motion. And if mu is constant on the trajectories, of mu f, then the trajectories generated by f, this one parameter group, is called the asymmetry of this system. All right. Let's take a look at reduction in a very familiar setting, namely mechanical systems. So we're going to look at how symmetries of mechanical systems allow us to reduce phase space. All right, so here we got m is r to the 2n. So it's the theory of a, if you like, a single point particle, point mass in a 2n dimensional manifold, or if you like n point particles, it's the same interpretation. So we're going to use the Darboux-Weinstein theorem to express some open set in this symplectic manifold in terms of Darboux coordinates. Well, it's hardly necessary. We already have the coordinates for this system. I mean, there's a little bit of content to this statement here. We're going to imagine we have some function f that's g invariant, or at least time invariant. And we're going to demand that our coordinate system isn't just your favorite Darboux coordinates, but that the nth one actually corresponds to this conserved function f. So you can always do this by the Gram-Schmidt process, starting off with that coordinate and then completing it to a symplectic coordinate system. And now we've got a coordinate system, we can express the Hamiltonian. In these coordinates, x1, psi 1 up to psi n. Then this coordinate psi n is an integral of the motion. What does that mean? Well, we have written it all out here, and also we learnt it earlier in the course. That's the case only if the trajectories of mu h lie on the hyperplane psi n is constant. Another way of saying that is the Poisson bracket of h with psi n is 0. But the Poisson bracket, because the symplectic, you're going to take the standard symplectic 2 form here, the Poisson bracket is equal to minus dh dxn. And so what does this tell us? Well, it tells us that h is really a function only of n minus 1 coordinates and n of these conjugate coordinates, psi 1 up to psi n. So we know at least that h doesn't vary with respect to xn. So we know that the dynamics lies on this hyperplane psi n is constant. So we're just going to choose a value now for psi n. Let's call it c. And we'll use Hamilton's equations to understand the motion. How is it now described using the information that we have? Well, it's described by Hamilton's equations. So there's the first n minus 1 equations coming from Hamilton's equations. Here's the next ones. And we're missing 2. The nth. What happens, how does xn vary and how does psi n vary? So we have enough information to say how they do vary. So just exploiting what we've observed here about psi n being a constant of the motion, an integral of the motion, we know that the change of psi n is 0, right, because it's constant. And we also know that the change in x must be given by dh d psi n. So it turns out that with this constant of the motion, we can define a reduced phase space in terms of fewer variables. And using that, and this reduced phase space is the orbit space corresponding to the symmetry. Just as the Marsden-Weinstein-Meyer theorem guarantees us. And we can go backwards. So if you solve the Hamilton's equations on this reduced phase space, then you can work out the corresponding trajectories on the original phase space. That's like undoing this point orbit projection pi. Introduce a reduced phase space, at least on this open set U. In terms of our original coordinates. So we define new open set in a lower dimensional symplectic manifold by the condition that these coordinates here have this form here in the original manifold. So you're allowed to put any old a you like for the nth coordinate as long as this tuple lies in the original open set U. And we can define a reduced Hamiltonian that only depends on these the reduced number of coordinates. And this reduced Hamiltonian is just defined by the original Hamiltonian. Right, because the original Hamiltonian still doesn't depend on xn, we know that. So we can define, this is well defined. And how do we work out trajectories of our original system? So we can work out trajectories of the reduced system, right? This has got fewer number of coordinates, fewer number of independent variables. So you could solve this system first, and then you want to work out what are the trajectories in the original system. What do the orbits look like along F? And the way to do it is you look for trajectories on the reduced system and then you integrate some equations to get the trajectories on the full system. The equations are in front of us. What we need to integrate this equation here to find out what xn must have been on the solve the system on the reduced space. You've spent the symmetry. You have a smaller system, smaller number of independent variables. Solve it there. And then you want the original trajectories. And how do you get them? Well, you just integrate this equation here. And that'll give you the remaining dependence on the variables xn and psi n. And this carries all the information about the orbit under F. This undetermined constant here. So I think this is a good moment to stop. In the next lecture, we're going to look at the geometry of the image of the moment map. So the moment map for Hamiltonian systems is just a function, right? It's the energy function. And it has certain geometrical features. It's always positive, right? As long as you choose the zero of energy appropriately. So the rather astonishing fact about the moment map is that its geometry is highly constrained, and it has very many additional properties that are certainly unexpected at the first sight. So we're going to take a look at those properties in the next lecture and quote some theorems and examples that illustrate the highly constrained and special structure of the image of the moment map. Okay, but for now, thank you very much.